All right, so this is the warm-up problem. We have this double integral, and we're asked to sketch R, where R is this region that we're integrating over, and then find A. So we notice that we're integrating dA, so this is going to be whatever region we're integrating over, this is going to be the area of that region. All right, so let's look at it, right? So what I just talked about in our review is this is our lower bound, R of theta, and this is our upper bound, R of theta. So our lower bound is R is equal to cosecant theta. And I always forget, I think cosecant is 1 over sine theta. I looked this up, so this is in fact correct, yes. So the lower bound is 1 over sine theta. All right, that's hard to think about. It's hard to know what this looks like, but one thing that I could do is I could convert this into Cartesian coordinates, and then I could have a much better idea. Well, when I look at this, what I can see is that if I multiply through by sine theta, I get r sine theta, right, is equal to 1. But r sine theta is y in Cartesian coordinates, so I get y is equal to 1. That's my lower bound, and that is easy for me to think about, right? That's a horizontal line at y is equal to 1. Okay, let's try to do the same thing for the upper bound. So we have for our upper bound, r is equal to 2 sine theta. All right, you can see I can't do exactly the same thing, but one thing that I could do is multiply both sides by r. Then I have r squared is equal to 2r sine theta. So here again, I can recognize y, and you might remember from the discussion worksheet that r squared is x squared plus y squared. All right, so this is the equation for my upper bound. All right. Okay, and so now we need to sketch this region, sketch R. All right, so let me erase and then we'll do that. All right, let's get sketching. So here is my y-axis, and here is my x-axis. Here is y is equal to 1, and so this is going to be my lower bound. I'll just abbreviate this way, lower bound, LB. There's y is 1, here's 0, and up here is 2. For this, I'm going to rearrange it a little bit. It's easiest to solve for x, so I can write this as x is equal to plus or minus the square root of 2y minus y squared. What you can see is that when x is equal to 0, this is satisfied either when y is 0 or y is equal to 2. This reaches a maximum when y is equal to 1 at x is equal to 1. And it's maybe not surprising that this ends up being a circle of radius 1 centered at y is equal to 1, x is equal to 0. This right hand is x is equal to positive square root of 2y minus y squared. And then this left hand side, so this is going to be x is equal to 1, and then over here is x is equal to negative 1. This left hand side is x is equal to negative square root of 2y minus y squared. Okay, so we're integrating over a region that looks like this. Sorry, because we're integrating in polar coordinates, we're integrating with respect to r. So we're integrating in this direction, radially. And so on. The idea is that all of these pass through the origin. All right, so this is our region R. Now we can double check that by coming up here and seeing, are these angles consistent with what I've drawn? So it says theta starts at pi over 4. Okay, so that's over here at 45 degrees going through the point 1, 1. And then it goes to 3 pi over 4, which is 135 degrees over here, which goes through the point -1, 1. So indeed, this is the region. Okay? So now we've sketched R, we've done part A. All that's left to do is B, find A. Well, I can look at this and I just know what it is, right? This is half a circle. The circle has radius 1. So it's going to be pi times 1 squared divided by 2, or just pi over 2. All right? So I know A is going to be pi over 2. But let's go ahead and calculate it from this integral. All right, let me give myself room to work. All right, so here I have A is equal to the integral from pi over 4 to 3 pi over 4. When I do this inner integral with respect to R, I get R squared over 2, or I'm going to write it as 1/2 R squared, and we're evaluating R at 2 sine theta and cosecant. So we're going to have 4 sine squared theta, that's R squared evaluated at the upper bound, minus R squared evaluated at the lower bound, cosecant squared theta d theta. All right, so that means it's equal to integral pi over 4, 3 pi over 4 of 2. Now I'm going to use, there's this sine squared theta formula that says, there's a trig identity that says sine squared of theta is 1 minus cosine 2 theta over 2. Okay, so this is a trig identity for sine squared theta. All right, d theta. And the reason I do that is that I know what the integral of -1/2 cosecant squared theta is. So the integral of cosecant squared theta is negative cotangent of theta. So I get plus 1/2 cotangent of theta evaluated from pi over 4 to 3 pi over 4. All right, so now I have to think about what this is going to be. So I get, this just becomes 1 minus cosine 2 theta. So the 1 I can integrate, and that's going to give me pi over 2. Okay, so when I integrate 1, I get theta evaluated at 3 pi over 4 minus pi over 4, which is just pi over 2. Then I am integrating negative cosine of 2 theta, which is negative 1/2 times the sine of 2 theta evaluated from pi over 4 to 3 pi over 4. Then I get plus, all right, well, so the cotangent of pi over 4 is 1, and then the cotangent of 3 pi over 4 is -1. So this becomes -1 at the end of the day. All right, so now what I have to do is look at this and say, what is the sine of twice this minus the sine of twice that? I always forget what sine looks like. So here it is, starting at 0. This is 2 pi. Here's 3 pi over 2. And here's pi over 2. So this is going to be, the first one is going to be -1, and then I'm subtracting 1 from it, so it ends up being -2. All of this is -2, times 1/2 is -1, times -1 is +1, so I get pi over 2 plus 1 minus 1 is just pi over 2 as I expected. All right, so that's how you do the warm-up problem.